I think it's 3 0 something.
It was probably like Tacoma's can run.
Yeah.
I think my least
Okay, 10,000 miles. First thing, take note of the sign here. So this will go, it's really quite straightforward, this quiz. I just want to make sure that you're learning how to write, what you have to write to get points on the AP test. So what I'm going to give you as a quiz is it's very straightforward. I just went to the buff, pink, and yellow packets, and I created simply 2 problems that were, how should I say, somewhat similar, like, to be fair, quite similar to problems in those packets. So there's just 2 of them on the quiz. The quiz is worth a lot because I won't give you very many quizzes, and the total quiz category is 15%. But it's very straightforward. So I just went and found a problem and kind of made it similar to like one of the ones in the yellow or the pink or the buff. And then what you have to do is you have to make sure that your answer follows the pattern that I've been showing you in the answers to each of those. So for example, this would be a pretty good representation of what you'd have to do on the quiz. You have to show something like, get out of the way, come on, like this. So the question is going to be the same that it was in the homework. It's going to say, use limits to analyze the continuity. And then the formula will be not exactly something from the homework, but to be fair, pretty similar. I'm not trying to make the quiz tricky in this case. It's not really a simulation of what the actual AP test is like. It's more just a check to make sure you're learning to do proper notation. And so you'll have 10 minutes to do 2 questions. We will be very strict on the time, so you get used to that, but 10 should be more than enough if you've done a good job on the homework. Basically, when we grade the quiz, you've got to make sure you have this, so you can show the grader that you know where you're headed. You've got to make sure you have to have either this line or this line. You can have both of them, but you don't have to. One or the other is sufficient. You've got to make sure you have to have the equal sign, otherwise it doesn't make any sense. You've got to find the correct overall limit. This section right here, so we're going to grade it like AP grades their problems. And what they would do is if the student has everything they're supposed to have in this section, they would get 1 point. If you're missing anything, you just don't get the point. There's no half points, there's no quarter points, it's like 1 or nothing. And so as long as you have this box, one of these 2, the equal sign, and the correct result, you get the point. Questions about how it will be graded? Yeah, please.
Can I get you?
Yeah.
Go ahead, Carol.
Then you move on. You have to have this. You don't really have to show any work for that. You just have to know that maybe f of a isn't undefined, so watch out for that. But you have to show the value of f of a, and then you have to have the proper conclusion. The proper conclusion would be to show this relationship and then state that because of that, f has a removable discontinuity at x equal a. So if you have all the purple, you get the second point. So the problem is only worth 2 points. And you're either going to get 1, 2, or nothing. So, and they're very strict. Like you can have a lot of good stuff, but if you're missing something, you just lose the point. So the purpose of this quiz, again, is not to like give you a problem you've never seen before, which is more like the AP test. This is just to kind of get you used to like understanding what you have to put down on paper to for sure get the points. Okay.
Did you say f of a equals undefined, and then like after say since this does not equal this, therefore it has a removable undefined, or should you have to say like however?
You don't have to say however. Leave that out completely. You don't have to say therefore. So if you just wrote that followed by that, and then you just put that. That would also be sufficient. You would get that purple point. Is that kind of what you meant?
Yeah.
Ish?
Yeah. That solves it, so.
Okay.
That's good.
Other questions on how it's related? Okay, cool. So, 2 questions. They follow, you've got to have this kind of notation. Make sure you go back and review the buff packet as well. In the buff packet, the way you write the answer was slightly different because it was critical that you check the left and the right limits. So make sure, like for example, if the quiz has a question kind of like this, they're going to check to see if you are finding left limit with proper notation, right limit, and therefore you know the overall limit. That would be 1 point. And then the second point would come in here, again finding the value of the function, knowing that the overall limit and the function's value are the same in this case, and then drawing the proper conclusion. That would be the second point. The quiz is only worth 5 points. I mean, it's not the points that matter. It's the fact that it's 15% of your grade. That's what's important. You get 1 point for just literally kind of like the AP test. Like everyone who takes the AP test gets a 1. So if you take the quiz, you get the point for showing a genuine effort. And then 2 points for one problem, 2 points for the other problem. Questions on anything? Okay, cool. If for whatever reason you take the quiz and, I don't know, like your mind blanks or something, and it just doesn't go well, you just come talk to me and we'll figure out a way to like have you do it again another time or do something else or whatever. I just need you to get the experience of like, okay, this is what AP is going to expect. This is how careful I have to be with my writing. This is a chance to prove that you can do it. That's all. So very straightforward. Questions? Cool. All right. So that's the quiz. That will not take place the next time you come to class, which is Wednesday due to the Labor Day holiday, but the time after that, so on Friday. So plenty of time to review those 3 packets and make sure you're ready. Right. So grab the new packet. Okay, so the topic changes completely. The rest of Unit 1 doesn't talk about limits at all, really. We might kind of mention it once in a while, but not directly. We're shifting our discussion to talking about another thing that will carry with us throughout the year. In fact, this will be carried with us throughout the year a lot more than limits were a part of the course for the whole year. Yeah, please.
Sorry, I was just wondering, so the quiz is on the 3 packets? Like
Just the 3 packets, yep. The buff, the pink, and the yellow. And I literally, I'm not trying to fool you at all. I went to those packets and I said, okay, I have to make sure that you can look at a problem like this, that you can remember what type of analysis you're supposed to perform, that you can remember how to use the proper notation, and then I just took a problem and just kind of modified it. So in this case, I'm not trying to fool you. I'm just trying to verify that you have the right notation. Does that make sense? And I just did that with 2 questions. So as we get closer to the actual test, which we are sneaking up on rather quickly, I will start to give you questions that are very different, and then you've got to use your knowledge of the rules to solve those questions. So that's more like the actual AP test. 2 points for Ellie. Okay, so back here, this idea we will carry this idea with us throughout the year. Many AP problems are going to ask you to study what I call the amount of something, and you're going to compare that to what I call the rate at which that amount is changing, and then what I call the rate at which that rate is changing. So those are my little abbreviations. But this does happen on numerous AP questions. Like, I can't overstate that. This is super common. for this example, we are considering the amount to be the position of an object. And the idea is that the object doesn't travel in any sort of like complex way. All the object does is go back and forth. So it makes the math a lot more straightforward. In fact, I had 2 students who graciously purchased a gift for me, and because I have this habit of standing in front of the room and walking back and forth and saying, I'm the particle, like, watch me, I am the particle. Like, the problem we'll talk about that on the AP test. A particle moves along the x-axis. And I'm like, okay, that's me, so you got me a hat. I don't like wearing hats, but I'll try. It's also not the best, most coolest hat in the world. It's kind of lame. But anyway, okay. So I got the particle hat. Then one year, 3 students decided that was how they'd dress up for Halloween, so they all got hats and wrote, I am the particle. It's a good Halloween. Anyway, so look at me. I'm the particle, okay? I only move in a simple way. I only go to your right, or I go to your left. Is everybody with me? Okay. The problems will literally say a particle moves along the x-axis. Look at me. Don't think x-axis like x-axis on a board. Think of x-axis as like this path that I walk along. Like, you have to keep them separate. The graph does not ever show you the particle. The graph only shows you a whole bunch of numbers. And those numbers are numbers that tell the story of what the particle is doing. But as the hat says, I am the particle. I'm walking here in front of you. That's all the particle does. It just walks. It sounds silly to say a particle walks, but whatever. The particle walks back and forth, okay? I can't wear the hat very long. I don't like hats. Pretty good? Cool. Okay, so the reason I say that the particle is the amount, it's not the particle that's the amount, it's the position of the particle. Those are 2 separate things. So, back to the hat. So, I am the particle. Very good. I see, the mistake I made was I would stand in front of the class for years and I would say, I'm the particle. And I move back and forth. And everybody got that. And then one day I said, it's like I need a hat or something. I would say, I'm the particle. It's like, I won't buy you a hat. Never mind. Okay. The jokes are falling flat as usual. Look, I'm the particle. The amount that I'm talking about isn't the particle. The amount is a number that represents the particle's position. And I call it an amount because it's just a single value. It's like, okay, consider the projector. Well, that's right. Just got busy all of a sudden. Consider the projector to be the center of the path along which the particle moves. So if I'm standing right here, I'm the particle. I have a certain position. We would say my position is roughly 5 feet from the projector. So I'm at position 5. It's one number. It's an amount. It's just a position. If I move, and I'm over here now I'm at like position -8. That's what amount means. It's the position of the particle. So memorize, if you're talking about particle motion, the position is what I'm going to refer to as the amount. It's just a single number. But it can be different depending on where the particle is. The particle is moving, that means my position is changing. Questions? Cool. And then this graph in blue, this will help as well. Grab your blue packet, tear off the very last page. There you go. And that's the graph we're looking at. Like, I always found it annoying as a student to have to sit there and flip the packet back and forth. So I designed the packet so that you could tear off the back page. Helpful? Good. And then just set it next to you like Ellie's got. Perfect here. There we go. Perfect. And there's a graph A, graph B. We're working on graph A. Try to make that really clear. You have mail for someone. Mark the roll before I forget. Let's see. Okay, so the blue graph shows various positions of the particle at different times. So the horizontal axis is recording time, and the y values are the positions of the particle. So when you look over here at this table, when I talk about the amount is not talking about time per se, although it is related to time because there's a different position at different times. Questions about anything? Perfect. Rate describes how fast the position changes. So the position is really one number. I guess you could think of it as two, because like I might be here, the time might be 20 seconds, and I'm at position 5. And then maybe at time 30 seconds, I'm at position -8. Okay, that's the position, that's the amount. The rate is how fast the position changes. So it's a bit more complex. Like, here we go. Let's get you to think, not just listen. I'll do my best to act it out. This is not the easiest thing in the world to do, but be patient. If I do this, it's very exciting. Okay, if I do that, just say yes or no. Is my position changing? Say it.
Yes.
Yes, cool. Raise your hand, please. At what rate is my position changing? Like when I did that, at what rate was my position changing? I'll do it again. Keep your hands up. At what rate does my position appear to be changing? Just make it kind of an estimate. I'm doing my best to be super accurate on this. What does it appear my rate of my, what rate is my position changing, Jackson?
Like 1 step per second.
Raise your hand if you knew that. 2 points, 3 for Jackson. And I was trying to go about 1 foot, but
Yeah.
1 step is very accurate. So we're like 1 foot every second. That's a rate. It's how fast my position is changing. 1 foot every second. Pretty comfortable? That's why I say it's a little more complex. Like position's simple. I'm at position 5, maybe the time is 20 seconds. But during this, I don't know, 5-second period, my position is now changing 1 foot every second. So, questions? And they give that a name, they call it velocity. You have to memorize the name.
Is velocity consistent through the graph? Always.
I'm not sure what you're talking.
Like would you ever like speed up or slow down?
Absolutely.
Yeah.
That becomes difficult to act out.
Right.
I can try. It's hard to like I need one of those like electric, like the 2-wheel scooter things you stand on. Yeah, that's what I need. That'd be cool. In front of the room,
Exactly.
I'd kill myself. That would work better. But yeah, no, we don't. It's very rare that we will talk about any sort of particle that is moving at a constant speed or a constant velocity. Almost always the velocity is steadily changing. That's what this graph is showing you. Yours isn't color, sorry, I don't have a color copy machine. The orange graph is labeled V of t. That's the velocity. And again, don't look at the orange graph and try to picture the particle. You look at the orange graph and you just see numbers. And the numbers tell you what the particle is doing. Like right through here, answering August's question, 2 more. I can find this dot. That's a certain velocity. It's about -10. I can go to this dot. That velocity is now about -38 or something. This velocity is now like -60. So yes, the particle's velocity is steadily changing. But yeah, okay, last one. The rate of the rate. That rate tells you how fast the velocity is changing. It's the rate at which the rate changes. That has a name, it's called acceleration. Okay? That one's really hard to act out. I won't attempt. Have to somehow, well, it's not that bad, I guess, but, so if I go like this, here we go, let's get you guys to think. Watch me. Raise your hand if you can tell me what is my velocity. Hands up, hands up. What's my velocity? Don't overthink it. I'm not trying to make it hard. Sadie, what's my velocity? So, sorry, Sadie said my velocity is 1 foot per second. How many agree? 2 points, 3 for Sadie. So, what's my acceleration? Hands up, hands up. What's my acceleration? Acceleration means how fast is my velocity changing? What's the rate at which my velocity is changing, Alicia?
0.
Alicia says 0. Who agrees? 2 points, 3 for Alicia. Okay. Do this one now. Rough. Go like this. Then go like this. Then go like this. Then go like this. I tried to exhibit an acceleration. You know what the acceleration was? That was rough. One more time. Acceleration describes how fast the velocity is changing. So watch. In the first second, what's my velocity? Say it. 1 foot per second. In the second, what's my velocity? 2 feet per second. Now my velocity is, well, I tried to do 3, but whatever. 3 feet per second. Now I tried to do 4. So, do you see what I did? So my velocity was 1 foot per second. Now my velocity is 2 feet per second. Now my velocity is 3 feet per second. Now my velocity is 4 feet per second. Hands up, what's my acceleration? Acceleration tells you how much the velocity is changing. Noah Norton.
On the off of 1.
It's exactly 1. Every time a second goes by, every time a second goes by, my velocity went up by 1 foot per second. That's why the acceleration would be something like this. This is the worst video ever because all they can do is hear me talking. There's nothing to look at. Sorry, I don't have a camera. My velocity is changing by 1 foot per second every time 1 second of time elapses. That's an acceleration. That's a rate at which the rate changes. Questions? 3 for Noah.
We're going to do like exponential acceleration. Or I guess that would just be the
We
rate.
just study whatever the heck they give us. So do they give us stuff like that? Yeah.
Is the velocity the y?
In all 3 cases, the time is always the horizontal variable. So when you look at a graph, you're always looking at a bunch of dots, and every dot always represents 2 numbers. Like right here, this dot is representing 2 numbers. It's representing a time of about 3.3 seconds. That's the horizontal number. And it's representing a velocity of about -60. I'm not sure that was your question, though. And then the acceleration is the same idea. At that moment, the time is still 3.3 seconds, but the acceleration is actually 0 at that moment. For this example on the board, that's of course not me walking back and forth. But if you want me to do this, good luck. That's rough to act out. I need the hoverboard for sure, and like a computer program to like make sure the hoverboard goes at the speed I need it. That'd be cool. I could do that for the summer. Exciting. Questions? Okay, cool. Some key things that you must memorize. So you have to memorize this relationship here. That we have an amount, we have a rate, and we have a rate of a rate. In this example, it's position, velocity, and acceleration. But it will become all kinds of different things as we do different stories.
Position, velocity, rate.
So position is the amount. The position of the particle is the amount. The velocity of the particle is the rate at which the position is changing. The acceleration of the particle is the rate at which the velocity of the particle is changing. Okay, next thing. You also will have to memorize this chart. This chart is unique to my class. There are calculus classes throughout the world. I suppose somebody else may have used this. I don't know. I never found it in a book. I had a student who invented it. Okay. Her name was Danika Wright. She was a student my very first year. And I saw her using this as she solved problems. And I instantly thought, that's really helpful. And so I just asked her, is it okay if I use this? And so it became Danika's chart. I just named it after her. It's not a math concept. She didn't invent that. She just kind of organized the idea of how the amount of something, the rate, and the rate of the rate are related. And we'll talk about what this means, but you don't need to have that memorized. So as we practice it, it becomes pretty easy to memorize.
I see.
Okay, this part here is important, of course. There's a difference between instantaneous velocity and average velocity. I already mentioned that velocity is the rate at which position changes. Instantaneous means how fast is, what is that rate at a given instant. Average means what's the rate averaged over time. So an average never takes place at a given moment. An average is over a time period. Instantaneous is always at a given moment. Some symbols that we'll start using, you'll need to memorize these. That's the symbol we use for velocity. This is the symbol we will use for position, although they'll also use some other ones. Sometimes they use S of t, sometimes they use P of t, sometimes they use H of t if the particle's going up and down. I've seen them use A of t for the altitude. Those symbols have all been used for the position of something. I've never seen them use anything, well, I guess rarely will they use anything but V for the velocity of something.
So for the amount they can use any of those four.
Yeah, they kind of can get creative as far as the amount, like for a moving object. For velocity, they tend not to get creative. They just usually use V. If they use anything else, they'll just tell you. I think one time I saw them use G or something, but they just said G represents the velocity. T for Ellie. The next part here we'll discuss kind of as we go along. This is kind of new symbols for you. You've likely never seen those before. Let's see. Average. You have calculated average rate of change for a long time. Average rate of change just means slow. But in this class, we calculate two different kinds of slopes. We calculate tangent slopes, and we calculate secant slopes. So tangent slopes are instantaneous rates of change, and secant slopes are average rates of change. So the tangent slope that we calculate, that's an instantaneous rate of change. If we calculate a secant slope, that's a average rate of change. Questions? Cool. So this should not look too unfamiliar to you. I want to find the average velocity. I need to figure out, on average, how fast is the position changing, or how much is the position changing, and then I compare that or divide by how much the time changes. So it's an old formula you use since about 7th or 8th grade, where you take y2 minus y1 and you divide by x2 minus x1. That's secant slopes. Questions? Okay, keep going. So the first page has these big concepts. First page has the Danika's chart. And then it has the equations that were used to create the graphs. For now, you don't have to worry about the equations. Eventually you will, but for now you don't. That's the equations that were used. And then it starts asking questions, so let's dive into the questions together. So first question says, use graph A to estimate the average velocity of the particle for the time period 1 to 5. So average velocity means, right here, this is my favorite version of the formula. You're free to memorize any portion of the formula you want. I like memorizing the little short piece. I think it's the easiest. I simply have to find, for this time period, how much did the position change? So I need to identify the position at both ends of the time period. So now all of you are going to look at your graph. You're going to find the graph that is showing the different positions of the particle at different times, and you're going to raise your hand and tell me what was the position of the particle. Just read the graph and do your best to estimate. What was the position of the particle at time equal 5 seconds? And raise your hand when you have it. Feel free to talk to each other if you want. But
Which pattern were you using?
so if you look at your graph closely, you don't have the color, so it makes it a little bit harder. You have little labels. So there's a label here that says A of t. That's referring to the red on mine. So this one here on yours, that's the acceleration. That's just a bunch of dots where every dot represents an acceleration. The middle one, this one here, this is the position. And then the bottom one here is the velocity. So what you're going to do is remember that the graph is just a bunch of dots. And every dot represents a position of the particle. So you follow the dots until you get to time 5. And then you identify using the graph, well, what was the position at time 5? And then just raise your hand when you can tell me what that is. Oh yeah, please go.
This is all three lines are showing one particle.
Correct.
It's just those 3 different elements of the particle.
Perfect. That it? Yeah, let me say that for the whole room. Hey, look up. No, very good. 4 points for that. There, again, and the lines are just dots. They're just numbers. But Noah's correct. What you see in front of you is you see a bunch of red dots, a bunch of blue, a bunch of orange. They're just a whole bunch of numbers that are talking about one particle. Like I'm the particle again. I'm not on the board. I'm over here moving back and forth. Okay? And then they record numbers about me. That's what's up here. It's like there's a bunch of instruments connected to me, measuring. Okay, where is my position at different times? Like what's my velocity at different times? In fact, as I teach, I actually do have quite an erratic pattern. Facing the floor back and forth like a jaguar. Okay, pretty good? So hands up, who knows the position of the particle at time 5? Show me your hand. Harder than I thought. It's okay. People just gazing off into the distance. Like, I don't know what he's talking about. So Emma, what do you got?
5, negative 160.
Negative 150.
50, 60, yeah.
Say it louder.
160, 150.
So in that vicinity.
Yeah.
So if you look at your graph, time 5 is right here. So the dot I'm focused on is right there. And based on the scale,
Aren't we looking for the velocity and not the position?
2 points for Caleb for asking. It says to estimate the average velocity, but what you have to remember is average means like what happened over time. And the formula here says we're going to find the average velocity, not by looking at velocity. We're going to find the average velocity by paying attention to how much the position changed. Delta means change. The triangle means delta. So we're looking for positions, not velocities. So she went here, and she said that dot has 2 numbers assigned to it. It has the number 5, which represents 5 seconds. And based on this scale, it looks like maybe 155-ish. So this is seconds. And in this story, this is going to be meters. Please raise your hand if you honestly did that before I wrote it on the board. If you didn't, that's okay. 2 points, okay. Then you need to talk through it again. So raise your hand. What's the position of the particle at time 1? Hands up. So you have to estimate. You can't read the graph perfectly, but hands up. I gotta get more hands. What is the position of the particle at time equal 1? Okay, we got better this time. Let's go, Sarah. What do you got?
1, 5, I don't know. Some slope.
So the time is 1. So you should have been looking about here. And then we're looking at the position dots, which means we're following all the blue ones here. So we stop about here. And halfway through the grid is 5. Sorry, halfway through the grid is 10. I'm going to say like -3 kind of thing. 3 for Sarah. Raise your hand if you got that before I showed you. Show me. 2 more. You want to? Yeah, please, Jackson.
So wait, look, why are we using the position graph when we're trying to find the velocity?
Yeah, that's bad.
Solid. Hold tight. We're almost there. No, keep asking. 3 more for Jackson. So Jackson, get ready to collect some points here as I talk with you. Are you comfortable that what we discovered was at 5 seconds into this particle's journey, its position is way over there?
Yeah.
Like it's very negative. Please look at me. The particle's not going like this. It's not going up and down. The numbers go up and down, but the numbers describe the location of the particle as it moves back and forth. So -155 means the particle's way over here on the left. Good. And then Jackson, you're okay that at time 1 we discovered, so 4 seconds ago, the particle was only at a position of -3 meters.
Yeah.
Good, 3 more for Jackson. So go to Caleb now. So Caleb, we just studied what happened at 2 different times. How much did the particle's position change during that time period?
Position by about 150 meters.
Close. If we use the numbers we have on the board, we would say precisely how much did the position change, Caleb?
Precisely. It's
Very good. So
yeah, I'd say like 152.
perfect. Yeah, it was at -3, 3 for Caleb. It was at -3. Now it's at -155. Look at me, visualize it. Like the particle's here, time goes by, it's way over there. Its position is different by 152. Negative, because it went to the left. So we've just found this thing. We found the change in the position. Now you're seeing it. We found the change in the position. So let's write that down. So we found, hold on a second. Okay, so we're trying to find the average velocity. And we're doing it for a time period from 1 to 5 seconds. Remember, the homework packets are your notes. It's really, you're keeping a nice record of what we talk about, so you have something to study for the test. So this is going to equal, we have the -155. We subtract from that a -3. This is a number of meters. We ended up with -152 meters. Questions? Hands up. How much time elapsed for the particle's position to change by that amount? Hands up. It's what, keep your hands up. It's what I'm trying to tell you all year long. Don't try to copy how I do the problems. That's not going to help. Understand how I'm thinking. Like, where's this stuff coming from? So Clark, how much time changed? 4 seconds. That's the 5 minus 1. So at this moment, you'd have to grab a calculator. Anybody have a calculator? Sweet. Go Spencer. What's 152 over 4?
38.
38 exactly.
Yeah.
And it's negative.
Yeah.
3 points for Spencer. Okay, we just used position and time, not position alone. We used position and time to calculate an average velocity. on average, if the particle was here and it ends up way over there, it's going to have to move 38 meters every second. It didn't really do that. It went back here. It went slow at first, and then went faster and faster and faster, and then it slowed back down. But on average, it went 38 meters every second. No worries. Two more, please, TJ.
So when we plug in the negative 152, wouldn't we use a positive 152 because it's just a change
Oh,
instead of...
awesome. Look up, look up, look up. Look, free. Everybody get this one. If my position is here, and 4 seconds later it's way over here, my position changed by 152 meters. I could have been here at location 3, and could have gone that way, and had my position changed by 152 meters. Just say it out loud really together. Are those situations the same or different? Say it.
Different.
Say it louder. Same or different?
Different.
Louder.
Different.
Kind of depends on your perspective, but for our class, different. Like, we want to get a little more detail. We want to understand the difference between, hey, did my position change to the right or did it change to the left? So the negative is important because it's telling me, hey, my velocity was negative, I'm going that way. Please.
Oh, I'm just wondering, why again is it that you're saying that it goes up and down, but it just goes left and right? Why is that again?
Wait a minute.
So what happens is, hey,
Velocity.
look, 3 for Ellie. Every student I've ever had makes this error. They look at the graph and their brain says you're looking at the particle. You're not. You're just looking at numbers. The numbers talk about the particle, but it's not the particle. Like this number here, like these numbers are going down. Through here. So these numbers, these positions are going down. Hands up. Look at me. In this time period, when you see all these numbers going down, the positions are becoming more and more negative. Raise your hand, please. Is the particle moving to the right? Is the particle moving to the left? Is it doing both? Is the particle going up? Is the particle going down? What's the particle doing? Let's go, Jared. I'm looking at Jared and calling on Josh. Sorry, Josh. What's Josh talking? Moving to the left. It's moving to the left because the position, the numbers are becoming more negative. The particle's not moving down at all. I'm the particle. I can't go down. I can only go right or left. I'm moving to the left. The graph just has numbers talking about what happened to me. If that helped at all. Okay, please.
So, like, it's the negative, whenever it's just negative, it's moving left, and whenever it's moving positive or more positive, it's going back to the right.
It kind of depends, but let me do an example that I think will answer your question. If not, you just ask again. Sorry. Right here, Clark. What's the position roughly?
-3.
Good. So the 1 is just the time. Everybody look. Like, the time is 1. That's not the position. That dot has, the coordinate of the dot is 1 comma -3-ish. But when I say the position, that's just -3.
Yeah.
Okay. What's the position about, we'll pick easy ones. What's the position right here?
-60.
Good. So if your position was -3, and then it becomes -20, and then your position becomes, I'm on board, -40,
They're just
which way are you moving?
left.
You're moving left. But come over here, watch this one. Your position is 100. Now your position is 80. Which way are you moving? You're still moving left. Hands up. What's the difference between these 3 dots versus these? Both times you're moving left. But there's a big difference between what this is representing versus what this is representing. Hands up. Come on. More people. It's all talking about the position. Like, what's different, Taylor, about the top 3 dots versus those?
It's just different, like, areas.
It is. These 3 dots are telling you, you guys get me all wound up, that your position is way over here on the left, on your right. It's over here. I'm at 100. And then some time goes by, and now I'm only at 80. Now I'm only at 60. So I'm moving left, but I'm over here on the right side of the center of my path. Please, Alicia.
If x is time, how is it negative on the last side?
So think of it as simply relative, meaning this is just when we decided to start keeping track. So it's just a second ago.
Okay.
That's all. Does that kind of make sense?
Yeah.
3 more. Anybody else? Yeah, please.
So we did the same thing with like finding the points on the graph, but we did it on the velocity line. Would that find the average acceleration?
Yes, absolutely. Look in your pocket. Take it for that one. Hey, here's what Spencer said. If you turn forward in your packet, I don't know how many pages, it's not very many. Flip 1 page at a time for Spencer. Right there. You should see a bunch of bolded formulas, just like on page 3, that look identical to the bolded formulas on page 1. That's because the relationship between the amount and the rate is identical to the relationship between the rate and the rate's rate. It's exactly the same. So the good news is you don't have to learn 2 things. You just learn one thing and then you just reapply it. If you look at Danika's chart, you'll see the same pattern. Look right here. That relationship is copied right here. Okay? So it's super easy to memorize because it's just a copy. So, please.
I don't really understand what's going on in that table.
Don't worry about that yet. Don't worry about that yet. Just 3 more, don't rush me.
You read letters on that too.
Yeah, I was like.
I would not expect you to know anything about that at this point, other than I named it after a favorite student. So, okay. Questions? Awesome. Okay. Other questions? I lost track of the questions. Are we good? Okay, I'm not sure I answered everybody's, but okay, cool. So we found the average velocity to be approximately negative 38 meters per second. That average velocity is only for this time period. You pick a different time period, you get a different average velocity. Caleb and Jackson asked, why are we using position? Did I answer that question? Okay, perfect. Go back to here. Woo! Got wound up, I don't know why. Okay, these are redundant questions. I put them on there just to make sure you understand they're the exact same thing. You don't need to write it twice. You just need to know that they're the same thing. Does that make sense?
So they're asking the same thing.
They are.
Average
And
velocity is just getting slower.
yep, and the way you draw that, Clark, is like this. You would draw a line from this time and position, dot, to this time and position, dot. And then if you calculate the slope of this line, the slope of that line is the average velocity. And what happens, Ellie, is they don't ever ask you 2 things in sequence like that. But what they do is one AP question will be talking all about secant slope. A different AP question will be talking about average velocity. And they don't tell you that they're the same. You have to know they're the same. That's why I put it on there. Yeah, please.
Would the answer technically be like about negative 38 because we had to like estimate?
Oh, absolutely. Yeah, they don't expect you to be able to read a graph like this perfectly. And if they gave you answers, none of the answers would be so close you couldn't tell. Like one of them would be either this exactly, or it would be close enough and the others would be further away to be like, okay, no, I've got the right one. That's a good call. Please.
Why did they say secant slope instead of slope? Is the
Awesome.
same thing?
3 more. And 3 more for Lincoln. Young. No, it's because there's 2 different kinds. Look at me. Secant slope is a slope between points. That's it. Just memorize that. It's the slope you've studied since 7th grade. Pick a point here, draw a line, find the slope. Before now, you didn't have to call it secant slope because there was no need, but there now is a need. Here's why there's a need. Look over here at these notes. Let's get this on top here. Hold on. Come on board. Okay, so we're on top now. Good. says instantaneous velocity. Instantaneous velocity is the tangent slope of the position. So now I'm going to show you something I don't think you've ever seen before. If I go to the velocity graph, let's pick a really easy one. Right here, raise your hand, don't overthink it, I just want to make sure you're thinking with me. I'm not trying to fool you. The time at that moment is 4.848. Raise your hand so you can tell me what the velocity is at that moment according to the graph. Hands up. According to this graph, what is the velocity at that time? There we go. Again, don't overthink it. Just read the graph. What is it, Grace?
0.
So Grace looks at that dot and says the y-coordinate of that dot is 0, which means they're telling me the velocity at that moment is 0. How many knew it before I said it? 2 points, 3 for Grace. Okay, that's the velocity at that time. The velocity number, this is Spencer's question, the velocity number is representing the tangent slope of the position at that moment. So if we go to the position graph at that exact same time, right here, we notice that the position graph is flattening out. If you were to try and find the slope, like if you try to zoom in on that spot and look at the graph, if you kept zooming in, it would stop looking like a curve. It would start to look flat. It's no different than if we walk outside, we're on the earth, we're not on a concrete platform. Raise your hand and answer this question. Out there on the grass, like theoretically, am I standing on a flat surface or am I theoretically standing on a curved surface? Hands up.
Earth is flat.
That's pretty funny. Hey, so, yeah, if it's the surface of the earth, we grade it and all that sort of thing, but the surface of the earth is curved, okay? 3 points for Aisel. Whatever. Okay, moving on. Funny. Look. Calm down. Okay. If you zoom in, the bottom of that curve will again appear flat. That's kind of the idea of tangent slope. Tangent slope is slope not between 2 points. Tangent slope is slope at 1 point.
What? The slope at 1 point. Continue to zoom in.
Let's rephrase what I said. This is why we study limits, actually. You can't really find the slope at 1 point because slope means find how the points are changing. So what you do is you find the slope between 2 points that are really close. Remember left-hand limit? And then you find the slope between 2 other points that are really close. And if those slopes appear to be becoming the same slope, then we say that's the slope at that 1 point. If you do that on a curve, like so, and we'll do a lot more practice of this, we'll discover that at this very bottom, that really is trending towards a slope of 0. If you do it up here, the 2 slopes on the other side are not trending towards 0. Did that help a little? Yeah. 3 more. Okay, cool.
So when you say getting really close, do you mean like the 2 numbers that are like basically the closest? So like
Infinitesimally close. Infinitesimally close. It's the whole reason we study limits.
Right.
Is to get that idea in your mind that, I can do this analysis where I just say, let's get closer and closer and closer and see what's happening.
Right.
And that was all done so you'd understand this. Go ahead, Taylor.
So if the tangent slope of a position, is it always going to be 0, the position?
So every velocity value, every number on this orange graph is representing the tangent slope on the blue graph. So right here, the tangent slope is 0, so this y-coordinate is 0. If I come up here, that velocity value is negative 60. That means the slope right here, that slope is negative 60. That's how they correspond. Please.
Is that the same with the velocity graph and acceleration?
Absolutely. Same idea again. Once you've learned one idea, you don't have to relearn it. You just reapply it. Three
Because I
more.
was wondering why on the velocity graph, if it's at 0, it's still accelerating.
But that makes sense.
Yep, so right here, this velocity, this dot is telling you the velocity is 0. But right here, Hannah,
It's okay.
take it for that one. Emma, her sister's Hannah. Emma, at that moment, is the velocity staying the same through this little time period, or is the velocity changing?
It's changing.
Definitely changing. If the velocity is changing, there is some acceleration. And I can tell you exactly what it is, right there.
Yeah.
So it's about 90. That's how you read these graphs. Please, Taylor.
So is instantaneous just mean like one point on the graph?
Say it one more time.
Instantaneous, like, for like these equations right here, does it just mean 1 point on the graph and then average is like in between, like a secant? Okay.
3 more. Just let me repeat back Taylor's observation because it was right on. Instantaneous means at an instant. That's where the word comes from. So instantaneous is at a given instant, a given moment. Average is over a time period. That's why instantaneous or tangent slope is slope at a point. Average is secant slope. So, questions? Ellie?
I was just wondering what these like equations were up here.
So those equations are just mathematical formulas that computed all of the dots XY pairs.
Oh, gotcha.
And so I just used a computer
It's just the
to
line.
draw every XY pair, and that became the blue graph.
Gotcha.
It's
This is kind of off topic, but the relationship between like the yellow and blue graph is like right when the blue stops speeding up and starts slowing down is when the yellow reaches its like amplitude or like its peak. And so,
keep going.
and so the relationship of the red and blue, is that kind of like the same as like when you're like that? I'm trying to remember. It's like the parabola rule where it's like 1 through 5.
I don't even remember that rule, so I can't really say. I don't know. 3 points though. Sorry. Clark.
So the derivative of the amount of that formula on the bottom right there, is that equal to the derivative of the rate?
So we haven't used the word derivative yet, but you're looking at it. Derivative means rate of change. If you calculate how fast the position is changing at any given instant, and we don't actually do it at an instant, we do what I talked to Noah about, we do it really, really close. That's the instantaneous velocity. So the derivative of position is the velocity. Yeah, if you've had physics, they talk about that as well. So. Okay, cool. Other questions on finding average velocity or secant slope of position? They're the same thing, basic question.
Just to think about the graphs, would we ever come across one that we would be measuring the particle's position with a jump discontinuity in its location?
Yeah. It's kind of hard to come up with a story where it jumps like that, but they do come up with stories. It won't be necessarily a particle. It'll be something like, hey, there's a pile of gravel and it's slowly changing height, and then all of a sudden they just make a massive dump. So it's like kind of like a quick step change. They come up with very creative stories. Okay. Next one. It says use graph A, so we're on number 3. It says use graph A to estimate the tangent slope of the position graph at the following times. And I probably put the times on yours, but I forgot to put them in. Yep, I forgot. So, that's my mistake. In this box right here, just write these in. You're going to write 1, 1.5, 2, 2.5. This should have been printed on the sheet, I just messed up. 3, 3.5, 4, 4.5, and 5. We're using that time period because it coincides with the calculation we just did. We just calculated the average rate of change of position from time 1 to time 5. Now it's asking you to find the instantaneous rate of change of position at each and every one of those times. So all you do is say, okay, this is the symbol for how fast the position is changing at any instant. That's the same thing as the velocity, which means I can simply, in this case, read the velocity graph. I can say, okay, at time 1, here's my velocity graph. That y-coordinate appears to be about -10. That means the velocity at that moment is -10. That's how fast the position is changing at that moment. At that moment, the position wants to move 10 meters that way in the next second. That's what instantaneous velocity means. Question? Please.
The yellow line is instantaneous velocity.
Correct. So every dot on the yellow or orange line is representing a specific velocity at a given moment.
And secant slope or average velocity has nothing to do with the yellow line. It has everything to do with position. Well, position over time.
I can't say nothing, but what we've done so far is what you just said, Noah. We've said, if I find the slope of this black line, which I'm drawing on the position graph, so move this out of the way again. So I draw a secant line on the blue. Like that. The slope of that line is my average velocity. But we won't learn how to do this for a while. Eventually, you will learn a method for taking every value of velocity on this orange graph, adding them all together, and dividing by how many you added up, and that will be the exact same number. So you will eventually know how to find average velocity 2 different ways. That's good. Math, there you go. Yeah. Science. That's what this table is trying to show you a little bit, is that if you go through and find the velocity each and every time, if you averaged all these, you won't get this number. Okay, like they won't be the same, but they'll be in the vicinity of each other. Because it's not a really good average, because you're not averaging every velocity, you're just averaging some of them.
And will the AP test ask you sometimes to find the slope using position and sometimes ask you to use it velocity?
Absolutely, and they won't tell you. Like you'll be presented with a situation and they'll say, find the average velocity. And you've got to say, okay, which method do I need to use? Yep, 3 more. Hands up, what goes in this box? Come on, hands. What goes here?
-22.
So that was a good hand, but you know.
Sorry.
They're okay. Enthusiasm is never a bad thing. Questions on that? Yeah, please,
It's like
Tim.
off by a little bit, doesn't matter.
Doesn't matter, because you're just estimating. If you look at the answers in the back, your answer may not match mine exactly, but as long as you can see you're pretty close, then you'll know you're doing the right thing. Does that make sense? Okay. Any other questions here? Trying to speed up a little bit.
That orange one?
It says use graph data to determine the time when the particle changes direction. Hands up, who knows that? We've actually talked enough for you to recognize that time, but maybe you don't see it. Once I show you, I think you'll go, oh, that's not hard. But I'm curious who can do it without me helping. Who can tell me the time when the particle changes direction? Got about a third of you. Let's go, TJ.
3.298.
Let's look at that for a minute. So 3.298 is right here. So here's the position graph. As we go past this time, the position is like -80. Now the position's -100. Now the position's -120. So say it as a class. Did the particle change direction as it passed this time? Say yes or no. No, it didn't. So that's not quite right. Hands up. 3 for TJ. Let's go. Chris, go ahead.
4.848.
So Chris says, look over here. This time, so now the position is, let's see, like -140, Now the position's about negative 155. Now the position's back to negative 1. Hey, that's it. That's when the particle changed direction. How many knew it before he showed you? 2 points, 3 for Chris. What would be the other time?
No, it wouldn't change directions. It would
Or like just,
No, but it's just going.
Oh, yeah.
Yeah, the particle, here's the quicker answer.
That was my fault.
Look, questions on that? Okay, the faster answer is the velocity will tell you which way the particle's moving. Because the velocity indicates how fast the position changes. So right here, the velocity is negative. That means my position is wanting to become more negative. The velocity, you can't really tell right here. It's a little hard to read the graph. I have a blown up version here. You don't believe it. The velocity never is negative in this picture until we get to right here. That means for all of the time where the velocity is negative, particle is moving left. When the velocity changes from negative to positive, the particle direction changes. That's what they're talking about in question 4. Questions? Okay, let's keep going. Oh yeah, please.
Wait, I'm just confused. How do you know which line we're looking at?
So if you look at your picture,
I thought, like, that's the line we're talking about.
so this is acceleration.
Yes. But like on this one, the time of
Right, so which number? You don't get number 4, right?
Yeah, just, I was just confused.
You're good.
on which one to look at.
You can answer question 4. You can actually answer question 4 one of 2 ways. You can answer question 4 by looking at the position graph and noting when the numbers on position, like these numbers are becoming more negative. Then they suddenly stop becoming more negative and start becoming less negative. That's the moment when the particle stopped going this way and started going back this way. It still has a negative position, but it's moving to the right. So I can answer the question using the position graph. More quickly, I can answer the question using the velocity graph. Because whenever the velocity is negative, I know the particle is moving left. When the velocity suddenly changes from having negative values to positive values, now the particle is moving right. Please, go ahead.
Okay, what does it mean with when the velocity, so in relation to the acceleration, let's go when it gets past, when the acceleration line gets past 0 and it becomes positive, what does that mean about the velocity?
When the acceleration is
So at
positive,
3.298, that point where it gets past,
whenever the acceleration is positive, it simply means the velocity is increasing.
okay, that makes sense, okay.
Okay. All right. As usual, really good discussion. We need more time to really get the rest of the concepts that are being used in this packet. What I would recommend is don't do, I wouldn't do any more. We want to just keep talking about the group packet. So I wouldn't do any more at home. You certainly can do whatever you need to do to make sure you're ready for the quiz, which is still a week away, but it is a big percentage of your grade, so I'm sure you get a good score. Again, if you don't get a good score, you come talk to me. We have ways to do a retake. That's what we do.
So how would you like write the answer to this question? Would you just say like add
Number 4. For number 4 really is a very common AP question. Like, it seems like every year they'll have something very similar to this. And I would write simply at t equal 4.848. I wrote that wrong, 848, sorry. T equal 4.848, v of t changes sign, or changes negative to positive. so the particle changes direction at that time. That's it.